Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Hey, step on inside, and we are in the Integrated Math 2 Big Ideas Math textbook, looking at section 3.2, graphing f of x equals ax squared plus c. Now, in the last section in 3.1, which you can find in my IM2 playlist down below, what you'll see is just graphing f of x equals ax squared. So every vertex of these U-shaped parabolas, these quadratic functions, they were always at the origin. But this plus c will change it. How so? We'll figure it out, but it's going to be some vertical translation. We'll see how that one works. It should make some sense, and coming forward after that, we're going to add a linear term and, just kind of move on from there. So hopefully you enjoy this video series so far, and let's see what we are going to do with the lecture portion of this to begin with, starting with, I don't even know what they're going to say. I don't know if you know this, but I don't look at this stuff beforehand either. So let's go and see what they say. But I know the information. You're going to graph quadratic functions in the form f of x equals ax squared plus c. So how does this plus c affect your things? And then solve real life problems involving that. They generally do the real life things, word problems. So graphing an f of x equals ax squared plus c, you're going to see that when c is greater than 0, there's going to be a vertical translation upward. You see this in green right here. So what you take is the original blue graph, and however many units c is, you go that many units translated upward. It doesn't go left to right, but that vertex shifts up, and every other point with it also shifts up. So what I'm curious to see is whether they use a table the entire time. They generally do, but you're going to see me not really use a table outside of showing how they use the table. So if this lecture helps you understand my connection with the material, then we can work off of that. But otherwise, I'm going to do the same thing that I did from the last one, with the exception that really we're going to be c units shifted up or shifted down. If this is ax squared plus c, but c is less than 0, then suddenly we're going c units downward on this parabola. None of these are narrower or wider. They all have the same a value. It's just that there's more growth that you see take place over this time because there are more x's that you can see y's for. So this red is never going to intersect with blue, which is never going to intersect with green. One just happens to be above the other and above the other during that time. So we're going to look at some examples of what they do. It looks like they do use a table, and I'm going to kind of connect the information with that table and see if it makes sense for us. Graph g of x equals x squared minus 2. Compare it to f of x equals x squared. When we talk about the comparison to begin with straight up, guys, when we see this minus 2, what's happening is every y value is going to be 2 less than the y values before it. The vertex will be 2 units less, but so will every other point. So before I even go to the table connection, because I'm going to connect how they use the table with everything, look at the points that they show us, the actual points here from this graph, compared to the ones that would have been on f of x equals x squared, like this, the original parent function. Now, how do these compare when you look at the same x's and the y's that associate with them? Well, as you can see here, this distance between blue and black is 2, 2, 2, 2, and 2. These are all 2 apart from each other. Every single black is 2 above the blue, or should I say the blue is below the black because we translated into the blue here. Everything's 2 units down. What you do is you square your x values and then subtract 2, right? So the y values become 2 less. And that's what's happening. This is a vertical translation, 2 units down. That's how I would describe it. I know they mention things like here's the vertex, all that. I'm only going to describe the transformation when I do. So let me find that. The graph of g is a vertical translation 2 units down of the graph of f. So that's what I'd be looking for the translation comparison. Now, how do they graph it? Once again, you heard it. You substitute values in for x, -2 to 2, whatever. It all depends on what you have. You've seen them do different things. And then what's in between that you don't see is, if I did f of x, let's see where I can fit this. I'll just write it over here. Let me get rid of their instructions, actually. Let me show you what f of x would look like and how g of x looks in comparison. So if I did an f of x, got to find a way to get that in front, though. There we go. If I did an f of x, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. Whoops, I wrote a 2. But 2 squared is, oh my gosh, 2 squared is 4. So how does this compare to these guys? Well, all of these are 2 less than that, right? So 4 minus 2, 1 minus 2, 0 minus 2, 1 minus 2, 4 minus 2. Subtracting 2 each time, and of course that's how they're getting their values. So what am I going to do in comparison? Well, what I'm going to do is, the thing that matters is how far apart these are from each other. They're the same distance away. This is still 1 away and 3 away, just like this is 1 away and 3 away. I'm going to still apply what I did last time, that 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, like that, and do it in relation to the vertex. If the vertex moves 2 units down and everything else moves 2 units down, then if I start from the vertex and do all my points, then I don't care what the actual y values are, I just care how far away they are from the vertex. So you're going to see that in other examples that I do if they use tables. We're going to start to make sense of that together. So I don't know if that made sense there, but as I start to connect them with other lecture portions, like, let's go and take a look at this one that also has a little bit more to talk about, but I can still connect it off with you. Graphing y equals ax squared plus c. Now we have an a value of 4 with a c value of 1. So this is not only a vertical translation, but it's also a vertical stretch. And actually the vertical stretch technically occurs first. You actually do this in order, whether it's alphabetical order, whether it's left to right order. If the numbers are part of the description for what you do, like translations and reflections and stretches and compressions and stuff like that, work alphabetically, work from left to right because of how they're written in order to affect your variables. So they mention already vertical stretch by a factor of 4 and vertical translation 1 unit up. It's no coincidence that they said the vertical stretch first and the vertical translation second. Anyway, how would I go ahead and graph this? Because you already have the points. You see the table. Hopefully you know what that means. Substitute an x, get out y. But how would I do this? I would actually start at the vertex, which is going to be, in the case, 0, c. If x still represents the 0 of the vertex and it's going to be the mid value of here, there's no horizontal translation on these, then plugging in 0 for x means this term goes away, and 0 plus 1 is 1. So we're always going to have a vertex, in this case at 0, c, as c is not going to be 0 these times. It's going to be plus 1 or minus 2 or whatever. I'm going to start 1 unit up, which is also the y-intercept. Now, everything that I do will be in relation to this value, this 1. So when I go 1 over, normally you just go 1 up to hit 2. Well, now I'm going to go 4 times farther up. 4 times 1 is 4. But plus 1 is 5. So when you see 1 comma 5, that's because I went 1 over and 4 up from 1. 4 up from 1. That's 4 times 1. When you go 2 over, I'm going to be going, instead of 4 up times 4, I'm going to be going 16 up from 1. 16 up from 1 is 17. Remember, everything is in relation to my vertex. And I hope I'm not losing you with that. The idea is that if it was at 0, 0, it would be 0, 0, 1, 4, 2, 16, etc. But now we add 1 to everything. Everything's shifting up 1 unit. And that's how this thing's going to be looking from my end. So whenever I plot my vertex, guys, you're going to have to treat that as your new origin, your new 0, 0. Though new y values for me do not matter. It's the distance from the vertex that matters, because technically plus 1 happens last, but we're applying it first with the vertex. All right, let's look at this next example where they have y equals negative 0.5x squared plus 2. And so that's the original. And then g of x equals f of x minus 7. Now, there's some stuff that we can do with this. What you're going to see, and I wonder how I'm going to do it in comparison, because I'm planning on not using a table. But what you have here is that f of x is this entire thing. So we take that entire thing and subtract 7 from it. That means whatever this graph was, which we might have to actually draw the graph, whatever this graph was, we now translate it 7 units downward. We take, where it's going to be g of x, instead of f of x minus 7, that's negative 0.5x squared plus 2 minus 7. And 2 minus 7 is negative 5. I can actually combine that. But the idea is this would be the new graph that I make. But in comparison to this, it's 7 units lower. Compared to this, it's a vertical translation 7 units downward. So as far as the graph goes, 0, negative 5 for the blue. Excuse me, let's start with the black, the f of x. 0, 2 is the not only the y-intercept, but also the vertex. And everything I do is in relation to the vertex. Because it's negative, I will be going downward. And instead of going, it looks like these go over by 2s. See, this isn't any fun because they do the scales. They go over by 2s. So instead of going 2, 4, because 2 squared is 4, we're going to be going half of 4, which is 2. Boom. Y half, 0.5. 0.5 times 4. Going 4 over, instead of going down 16, we're going to go down half of 16. Half of 16 is 2, 4, 6, 8. And that's where they're plotting those. The blue is the exact same thing, but translated 7 units farther down. So we start at 0, negative 5, and the same thing. 2 over, instead of 4 down, we go 2 down. 4 over, instead of 16 down, we go 8 down. And the scales aren't quite there. I'm going to be doing them with my graph paper that I had before. That'll be attached down below if you want to use it. So they have more examples there. I'm going to make sure to do them in the problems themselves. Solving real life problems. Let's see what the heck they have to say about this. The function f of x equals 16t squared represents the distance in feet. A dropped object falls in t seconds. The function g of t equals s naught represents the initial height in feet of the object. So whatever the, this we've seen this a lot before, negative 16t squared. I'm just going to point that out, negative 16t squared. That has to do with gravity. It has to do with force of gravity. That's all I'm going to say. So when that pops up, they're talking about that's how fast an object drops if you let it go. In general, gravity is going to take form. But if we add some height component to this, instead of dropping it from right here, if I drop it off a building, and the building's 100 feet high, or in this case 64 feet high, we're going to add that 64 as part of the height measure, and that's what S naught is all about, that g of t. So our full equation, our function will be negative 16t squared plus 64. That 64 lets us drop it from 64 feet up, and the negative 16t squared allows gravity to take hold and have this object speed up as it goes down to the ground. Common error. The graph in step 1 shows the height of the object over the time, not the path of the object. Oh, yeah. So one thing I've pointed out before, like this, some people think that, when you see this drop right here, that you're thinking, hey, what is this, an egg? That this egg is thrown outward and it does that? No, the egg is dropped straight down, but what's happening is time is going on. This is not X as in a position, how far out it goes. It didn't go out 2 feet or 2 blocks or whatever, anything like that. This took 2 seconds to drop, and there's more to solve for that we'll talk about, but this isn't going outward necessarily, it's just dropping downward. So here's the height over time. So 2 seconds later it hits the ground. How do we know? Because they graph it, and they graph it to the point that they hit the actual y-intercept, or in this case when the height is 0. They're asking when it hits the ground, I imagine. Find and interpret this thing. We talked about that. An egg is dropped in a height of 64 feet. How many seconds does the egg, after how many seconds does it hit the ground? We can graph that and find out where it hits which point it'll hit. You plug in values, I guess, until it works. Suppose the initial height is adjusted by k feet. How will this affect part B? So I'm going to answer that before we look at it. If it's adjusted by k feet, we add that k feet to it. If we raise our hand 5 feet higher, then we're going to add 5 units to it. If we lower it 5 feet, we're going to subtract 5 feet from it. Add negative 5. So what's going to happen is you have your negative 16t squared plus 64 plus k. And that should show up right. A gets the ground. When the initial height is adjusted by k feet, the h is translated up k units. Oh, the graph of h is translated up k units when it's greater than 0 or down k units when it's less than 0. So we're going to either add k or subtract k based on how high or low we adjust it. And they ask, oh, how will this affect part B? So they mention if we raise the height, it's going to take longer than 2 seconds to hit the ground. If we lower the height, it's going to take less than 2 seconds to hit the ground. Okay, so that's all that they cover there. Hopefully those examples made some sense, and hopefully I can make more sense of them when we do the problem sets. Let's start with the vocabulary and core concept checks and try and answer those 2 questions. Then we'll do the problem set, which is 1 through 41. State the vertex and axis of symmetry of the graph of y equals ax squared plus c. So I had mentioned this. There is no horizontal translation here. There's nothing that's affecting that when I plug in 0 for x, that it's still going to be the absolute lowest, or in upside down graphs, the absolute highest that we hit for the vertex. Therefore, when I plug in 0 for x, I get c for y. This also represents the vertex of this thing. Whether c is positive or negative, that's how much we go up or down, and that is going to be the vertex of these graphs. The axis of symmetry always goes through the x value of the vertex, so in this case it is still x equals 0. That has not changed. The axis of symmetry is when you have a parabola, there's a dotted line that goes through there, and because there's no horizontal translation, then we still stay at x equals 0. The absolute maximum or minimum is at c, however, for y when we have those. Number 2, how does the graph of y equals ax squared compare to the graph, plus c compared to the graph of y equals ax squared? This thing, I'll type this one out. It's c units taller or shorter, higher translated. Let's see, how does it compare? We translate c units up, down, depending on its sign. Now, they say more about that. I'll put that in parentheses. Positive equals up, negative equals down. So hopefully that kind of makes sense with what we're talking about there, the plus c. If c is -2, then it's -2, then we go 2 units down, things like that. But it's just a translation, otherwise everything else seems to be the same. So those are those quick ones right there. We are going to go ahead and move forward, guys. So get your stuff ready. If you want to print out the graph paper on PDFs, I'm sure we're going to have tons of graphs to talk about. I'm not going to use a table. I'm going to start from the vertex and do the exact same thing that I did in section 3.1. But once you have your vertex, only think about how far your points are from the vertex. Don't think about the y values themselves. If you can't think in those terms, then this won't necessarily help you. Go to a table. I'm not stopping you from using a table. Just know your order of operations if you're going to do something like that. Okay, so without further ado, let's go ahead and move forward. We are going to start graphing the functions in numbers 3 through 6 and compare them to f of x equals x squared. Now, what I've mentioned by comparing them to f of x equals x squared is that we are actually going to be only mentioning basically translations unless they do something else. And A, vertical stretches, compressions, and reflections. But C is only a vertical translation. It's not a horizontal one. I won't be talking about the new vertex or anything. It'll just be on my graph. I hope that's okay. So on number 3, we're going to be looking at g of x equals x squared plus 6. So f of x equals x squared, I'm going to go ahead and leave right here. This is at 0, 0. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. And if you reflect across the axis of symmetry, we go 1 unit away, 2 units away, 3 units away from that axis at the same height as before. This is our f of x graph that we're going to compare to. Now, I could copy and paste this graph, change its color, and say, what, ta-da, that's g of x, and there would be nothing wrong with that. In fact, I might give you a little look-see of exactly what that looks like. So if I took this whole thing right here, I copied and pasted it, say I turned it blue, and say this is going to be my g of x graph, guess what? Where does this graph go? This goes up 1, 2, 3, 4, 5, 6. This is what this next graph is going to look like. So that's how I'm going to end up doing them. Now I'm going to draw it again myself for you guys. But this is what we end up doing with these graphs. What we do is we take, change the color, is we are going to translate 6 units up to begin with, plot the vertex there. But everything I do is going to be in relation to the vertex. A is still 1. I'm going to go 1, 1, 2, 4, 3, 9, because that's what quadratics do, but from the vertex. The distance from the vertex. So let's go ahead and do that ourselves without any of that in the way. Let's go ahead and erase all that. And let's graph that ourselves, the same exact thought. So we start at 0, 6 because 0 for x, 6 for y is the minimum. That is our vertex. We don't have to do anything other than graph it. When I go 1 away, I go up 1 squared. Notice I don't go up 6 squared. 6 squared is 36, but we add last. We added first. We're doing everything in comparison to what we add last. Go over 2, we go up 4. 2 squared is 4, like that. And left 1, 1, and 2, 4. Now this, like I said, this all ties in to the 3.1 graphs. If you need to play catch up, go ahead and take a look at my 3.1 graphs and what I'm talking about with that. 1 squared is 1, 2 squared is 4, and how that turns out to be. But that's what it looks like. Okay, let's describe this thing. It is a vertical translation 6 units up. You kind of saw that from the beginning. Vertically translate 6 units upward. That is number 3. Okay, I get to move kind of faster now that we've seen those because these are all the same. These all have the same kind of appearance to them here. I don't think I'm going to draw the f of x each time unless I already have it copied and pasted. So we could, but I'm probably not going to. So number 4, we have h of x equals x squared plus 8. Now that plus 8 means everything's translated 8 units upward, including that vertex. 1 squared is 1, and negative 1 squared is negative 1. 2 squared is 4. That already can't fit. 11, 12. It's already up there. So I'll do what I can on the graph. Obviously, they would probably use a different appearance of a graph, but that's mine. And there's my parabola from that one. We vertically translate 8 units upward this time. Keep doing that. That is number 4. Number 5. P of x equals x squared minus 3. So minus 3 means everything's going to be shifting down 3 units, which could be just the description portion of that. But as I go ahead and graph it, This is going to be down 1, 2, 3 for the vertex, and everything's in relation to the vertex. 1, 1, 2, 4, 3, 9. 4, 16, I can't quite fit. 4 squared would be 16. You might wonder how I do some of that stuff so fast. You have two options. None of mine did I actually count 9 upward from here. I didn't actually do that. What I said was -3 plus 9 is 6, or it's 5 away from 4, right? I go from 1 to 4 to 9 from down here. So 4 away from down here is 3 away from here, and 9 away from down here is 5 away from there. So it's either a count or an addition. I'm not actually counting 9, though. So there's that, in case you're wondering about my speed. And sometimes I know whether it looks on or off because I've done a lot of quadratics in the past. To me, it almost looked like it was too far out, but I trusted it with the numbers. And smooth curve, smooth as I can get. Okay, so this is vertically translated 3 units downward. Like that. And then number 6. Number 6, we have q of x equals x squared minus 1. We are going to go ahead and graph that guy. We start at 0, -1. And we again, over 1 up 1. Over 2 up 4. Now what's 9 away from -1? That's 8. So over 3 up 9. And we can, of course, go across the axis of symmetry just like that. 1, 1, 2, 4, 3, 9. Okay. And there is the graph, and this was vertically translated 1 unit downward. Okay, so those didn't have a different A value. I assume these next ones will. Yes, it looks like they do, so let's go ahead. And they're a lot nicer with these A values than they were last time. Last time they're like -0.004, and like, I know what they were doing, man. They really said, hey, we got to stretch out these problems. They did. In exercises 7 through 12, graph the function compared to f of x equals x squared, so still the same thing. I'm once again not going to be graphing the x squared function, but imagine what 1, 1, 2, 4, 3, 9 was all about in relation to our vertex. The difference is now that a is not necessarily going to be +1 anymore. So now we have to see how it changes things. So we start with, at least I start with the vertical translation 3 units upward to say everything's in relation to my vertex. Now normally I'd go 1, 1, 2, 4, 3, 9 from here, but a is -1, which means there's a reflection over the x-axis, which technically happens first. We technically reflected first and then we translated next, but I'm already keeping that in mind, what I'm going to do as I translated 3 units up, because everything I do is in relation to my vertex. So as I'm translated 3 units up, I'm already reflected in my mind. We are going to go down. Instead of 1, 1, 2, 4, 3, 9 upward, it's 1, 1, 2, 4, 3, 9 downward. So we hit these points instead, going this direction, like that. So it did reflect over the x-axis to begin with. That was its flip, and then the translation happened next. Remember, when you plug in a number, you first square it, then you multiply by -1, and then you add 3. But if I add 3 on my graph from the get-go and account for the fact that it's going to flip over, then I'm all squared away. No pun intended. Okay, there is that one. So 2 things happen here. There is a translation, but that doesn't happen first. We reflect over the x-axis, in the x-axis, over x-axis, and then we also vertically translate 3 units upward. Okay, that's number 7. So yeah, I mean, maybe I should do this once, just that f of x thing. Just keep in mind the graph would have originally, been like this. Terrible. I'm not going to do the whole thing. Would have originally been like this. So we flip it over, like, boom, right? It flips over, boom, and then it goes 3 units up like that. Okay, so that's the idea. Okay, number 8. I had a cheesesteak earlier. What did you have? All right, number 8. It wasn't one of those small ones either. It was an 18-inch. Negative y and fries, cheese fries. H of x equals -x squared minus 7. Once again, flipped over in some capacity. There we go. We're going to translate this thing 7 units downward, be in relation to there for the vertex, and then we go downward from here. Negative x squared means flipped over. 1, 1, 2, 1, 2, 3, 4, a little bit off the map, but I want something else to fit with it, so I'm going to go ahead and apply that. And that's about as much as I can do for my axes, for my window. And there is that graph. See, they say compare to the graph of f of x equals x squared. That's in a description. I don't think they're requiring me to actually draw it. But we do reflect over the x-axis. Then we vertically translate 7 units downward. A and then C. A and then C. All right, number 9. Number 9. S of x equals 2x squared minus 4. Okay, the negative 4 is our vertical translation. I'm going to start 4 units downward like that. This 2 is going to be a vertical stretch component. Remember, we stretched first, translated second in our mind for transformation rules. Because, listen, the reason why we say that first, the reason I keep saying that first is because I don't go 4 units and then double everything. Otherwise, it would hit negative 8. But no, it's negative 4. We double first, and then we move it 4 down. We move everything 4 down. But everything's moved 4 down. So 1, 1, 2, 4, 3, 9, 4, 16. That's what happens when you square those guys. Not today, because after we square it, we're going to multiply it by 2. Vertically stretch it. Not 1, 1, but 1, 2. Vertical stretch. Not 2, 4, but 2, 8. Not 3, 9, but 3, 18. And that's off the graph a little bit. So I'm not going to fit that one. Everything's vertically stretched by a factor of 2. Everything's twice as tall. So it's going to look like this right here on that side and that side. And then we have a vertically stretched parabola with arrows and all. Domain still all real numbers. Range is y is greater than or equal to negative 4. So we are vertically stretched by a factor of 2. And then we are also vertically translated 4 units downward. All right, number 10. Number 10 has 3 things going on with it, just with an A and C, but the A has 2 parts alongside of it. T of x equals negative 3x squared plus 1. Okay, let's go. So the plus 1, once again, is a vertical translation of everything, all points including the vertex. We start up here. The negative is going to flip this over. Instead of going up as we go left and right, we're going to go down as we go left and right. This is a maximum value as it goes downward. How much? No, not 1, 1, 2, 4, 3, 9. We got to triple our values. Instead of 1, 1, it's 1, 3. Boom, 1 times 3. Instead of 2, 4, what is 4 times 3? 12. We're going to go 12 down from 1, which is negative 11. That goes a little bit off the graph right there. So same thing on this side, and this side just like that. And that is the graph where 3 things happened. We reflected over the x-axis, we vertically stretched by a factor of 3, and we translated 1 unit upward vertically. So we reflected over the x-axis. That's what flipped it over. We vertically stretched by a factor of 3. And then we translated, we vertically translated. I don't think you have to say that, but we translated 1 unit up. Upward. Translate 1 unit upward. I guess you don't have to say vertical, but I want to remind you that that is a vertical translation on all of these. As long as you say the word up, I guess. Number 11. Number 11 has an interesting fraction bit with a compression. We'll work around it. We have p of x equals negative 1/3 x squared minus 2. The negative 2 will be our vertical translation for our vertex. Hopefully you're getting a little used to that. So negative 2 here. It is negative, so we will be going downward instead of upward, but we will be taking 1/3 of our values. Instead of over 1 down 1, we'll be going down 1/3 of 1, well, which is 1/3. Over 2 instead of down 4, we'd be going down a third of 4, which is 4/3. If some of the numbers get a little strange for you to do, that's negative 1 1/3, then you can skip some of them. The easy ones that you want to do are ones that are really factors of 3. The numbers you can divide by, the numbers that are divisible by 3. So when I go over 3, 3 squared is 9, but we're going to go down 1/3 of 9. A third of 9 is 3, evenly. 1, 2, 3, just like that. So maybe 4 and 5 is skip. Over 4, down 16 thirds, that's 5 and a third. 20 down 25 thirds, that's 8 and a third. 36 thirds is down 12. Sorry, that's 6 squared. Over 6, down 36 thirds, that's down 12. Now I actually can't fit that. So maybe, maybe I do have to go on the fraction bits a little bit if I want to be actually clean. So down 16 thirds, 3, 4, 5 is down 5 and a third like that. And down 8, what did I say, 25 thirds? Down 8 and a third would be 5 over, because 25 over 3, so down 8 and a third like that. So if you want to make it look smooth enough and fit them, great. But the only real great numbers were over 3 and down 3. Down a third of 9. Okay. At least they can fit in that window range. So we are going to reflect over the x-axis. We are going to vertically compress. Is that our first compression? Yep, by a factor of 1/3. And we are going to vertically translate 2 units downward. Okay. And then number 12. Maybe I don't have to graph for a while after this. We'll see. Then number 12, q of x equals 1/2 x squared plus 6. One less thing to kind of talk about because we don't have to reflect. But we still have to compress. 1/2 x squared plus 6. I think I might like my 1/2s a little bit more. This problem might be a little cleaner than number 11. So 1/2 x squared plus 6. Well, we do have to start up here. 6 units up translated. Instead of 1, 1, 2, 4, 3, 9, let's go up half of those. 1, half of 1. 2, half of 4. 3, half of 9. That's 4.5. And that's all I can really fit. 1/2. 2, which is half of 4. 4.5, which is half of 9. So don't get to fit very many points, but I got a couple of them. More than I would from just an x squared. Okay, excuse me, no reflection over the x-axis, but there's a vertical compression. Factor of 1/2. We also vertically translated 6 units upward. Okay, so those are the descriptions of those guys there. So, any questions? Good. I don't know. You're probably like, I have several questions. All right, numbers 13 to 16. We're going to describe transformation from one to the other, and then we're going to graph them together. So this time it's actually more graphs than it was before. But maybe I get to apply one of them and do a copy-paste job, whereas you might have to do both. I don't know if I can cheapen you out that way. We'll see. Maybe for one of them. Number 13, we have, and I'll write them as different colors, f of x equals 3x squared plus 4. And then g of x, in blue, equals f of x plus 2. So I'll do this. I'll make f of x black to begin with here to kind of remind you of what we're actually doing. G of x takes f of x thing and makes it plus 2. So g of x instead, with that f of x plus 2, f of x is 3x squared plus 4. We're going to take 3x squared plus 4 and add 2 to it. So 3x squared plus 4 plus 2, 4 plus 2 add, and you get 6. You get 3x squared plus 6. So what's the difference between this guy and this guy? They both have 3x squared. This isn't a parent function, but this is the original function we do this off of. Comparing them transformatively, that plus 2 means like it does for plus c. It's a vertical translation. You move it 2 units further upward than the previous graph. So when it comes to drawing those graphs, what we're going to have is f of x look like 3x squared plus 4, which is a vertex at 4, and then 1, 3. Remember, we triple our heights. 2, 12 would be next, which I can't fit. So this is just going to be a basic, like this right here. And then the blue one for, so that's f of x. The blue one for g of x is going to be the same thing, but just 2 units higher. So we start at 6 and 1, 3 from there. Now my graph isn't scaled perfectly, but it's just going to look like that now instead. So what's the difference? This thing is translated up 2 units from f of x. So translate vertically, translate g of x 2 units up from f of x. Write an equation that represents g in terms of x. So that's what I did here. That was the thing I did. Okay, that's number 13. Number 14. We have f of x equals 1/2 x squared plus 1. We're going to take that same thing for g of x. We're going to take that f of x, and we are going to be subtracting 4 to it. So that means that g of x will be 1/2 x squared plus 1, the f of x equation. And then let's do minus 4. Now 1 minus 4 are the parts that combine. That's where we get negative 3. So it equals 1/2 x squared minus 3. So once again, no change in what we're doing outside of a translation. They ask us to describe the transformations first, as if for us to know that it's only a vertical translation. We vertically translate g of x 4 units down from f of x. Now, it ends up being at negative 3 on the vertex. So you're like, Mr. Robinson, wouldn't you say translate 3 units down? Well, we're not describing compared to the original parent function that would have been, f of x equals x squared. This is x squared, 1/2 x squared plus 1. So it's already translated 1 unit upward. And when we go 4 units down from 1, it's negative 3. So the original f of x would be 1/2 x squared plus 1. We start at 0, 1. We go over 1 up half of 1, over 2 up half of 4, over 3 up half of 9, and over 4 up half of 16. Half of 16 is 8. So we get a nice looking curve like this for black. Now the blue one, g of x, will look just like this, only 4 units lower. So I could literally do a copy-paste job. Maybe. But because I can probably fit more points, I'm going to go ahead and try and do so. Just let me get a better looking curve out of that. That's okay. All right, so that's f of x. G of x will be, again, it'll just be translated for, literally, here's what you could do also. You could say, here's this point. Let's go 4 units down. 1, 2, 3, 4. Here's this point. Let's go down 1, 2, 3, 4. This point down 1, 2, 3, 4. I got to take a sip of water from this cheesesteak. Okay, I'm back. So, yeah, all I'm doing is I'm showing, hey, everything's 4 less than it was before. That's kind of a thing. So 4 down from here, 4 down, 1, 2, 3, 4. Now let's confirm that these are actually working out the way we wanted to. From the vertex 0, 0, or not 0, 0, from the vertex 0, negative 3, I'm going to go 1 away and half of 1, 2 away and half of 4, 3 away and half of 9, 4 away and half of 16. What's half of 16 is 8. What's 8 up from negative 3? 5. Can I fit 5 up? 5 away and half of 25. 25 is 5 squared. Half of that is 12 and a half. So 10 up would be 7, and 11, 12 and a half, like that. So I can actually fit a 5th point there. Let's go ahead and reflect those over just like this. Boom. Pretty complete graph overall for both of these, f of x, g of x. And I already described the transformations. So this is translated 4 units downward. Remember, it is not wider. It does not hit more x values than the other one. This is just in our window range. And yeah, that works. Looks pretty good, actually. All right, that's number 14. Let's look at 15 and 16. Number 15, f of x equals, more of the same. F of x equals negative 1/4. Negative 1/4 x squared minus 6. And g of x equals, let's take that f of x and subtract 3 to it. So, that's not going to be a very decent graph because of how low it's going to go, but we'll have to make do. Minus 3. So, g of x, we take the f of x equation, negative 1/4 x squared minus 6. And then let's subtract 3 to it. Negative 6 minus 3 is negative 9, so we'll get g of x equals negative 1/4 x squared minus 9, which of course is just 3 units translated down from the f of x graph, which is all that I need to describe. We vertically translate g of x 3 units down from f of x. Okay. So f of x equals negative 1/4 x squared minus 6. Minus 6 is right here. The negative 1/4 means we will go down. Negative 1/4 means a quarter of our values. Over 1 down a quarter of 1, which is 1/4. Over 2 down a quarter of 4, which is 1. Over 9 down a quarter of, over 3 down a quarter of 9 is 2 and a quarter. And over 4 down a quarter of 16, which is down 4. So I'm going to fit as many points as I can plot on this one. The g of x equation, I won't be so lucky, because it starts at negative 9. So maybe this one I'll just do a copy and paste and just say that's as best as I could get with regard to just that workload. So g of x would be this same graph, but blue, and translated 1, 2, 3 units down, just like that. So that way they have that same kind of appearance. This one is negative 1/4 x squared minus 9. We start at 0, negative 9. It's that negative 1/4, just like that. We translated. We have the equation. We are good to go. I know you'd have to do a little bit more, but see where they go. 1 down a quarter, 2 down 1, right? That's a quarter of 4, like that. And then number 16, y equals 4x squared minus 5. This will be plenty vertically stretched. So number 16, f of x equals 4x squared minus 5. G of x takes the f of x and adds 7 to it. F of x plus 7. So that'll be g of x equals 4x squared minus 5 plus 7. By the way, what I'm writing in black is the f of x. You're probably supposed to be using parentheses around this, because if I had to do 2 times it or negative that or whatever, it would affect the whole thing. But negative 5 plus 7 is 2. I can actually write that now without parentheses. So it's 4x squared plus 2. Okay, so these graphs, that's right, I copied and pasted that guy. These graphs are going to look like f of x is 4x squared minus 5. We start down here at 0, negative 5. Over 1 up 4. 4 times 1. Over 2 up 16. 4 times 4, right? 2 squared is 4. Times 4 is 16. From here. 16 up from negative 5 is 11. It doesn't really fit, but I want to get it because I think that it's really close enough, and I want to get as accurate as I can for the first part before I do the translation of the next. Now, the other one's translated up 7 units. I won't be able to fit the second set of points, but I can get the first set, and I can just stay within here. I think that's going to work. This is not the best looking curve. Sorry about that. There, that actually looks a lot better just by doing that a little bit. G of x equals 4x squared plus 2. Now it's 7 units up. So is the next points, over 1 up 4. These are also 7 units upward from the other points with the same x values, and that's all I can really fit. And it's going to look like that for my g of x. Okay. All right, that is number 16. Not even halfway through. Number 17, error analysis. Describe and correct the error in comparing the graphs. So we have y equals x squared and y equals 3x squared plus 2. It does look vertically stretched, and it looks like it's 2 units upward, so there's nothing wrong with the graphs. The graph, oh, it might be this. The graph of y equals 3x squared plus 2 is a vertical shrink. Well, it's not a shrink, by a factor of 3 in translation 2 units up of the graph of y equals x squared. It looks like it is a vertical, oh, they probably mentioned, I think we had a problem like this before. They're probably thinking about the shrink in horizontal sense. We're shrinking that way. It became narrower. And that's definitely not true in this scenario. Even if it did, they said vertical. So the 3 is a vertical stretch. So they mentioned a vertical shrink instead of vertical stretch. Remember, I used the word compress, but that's okay. Compression. Instead of a vertical stretch by a factor of 3. And that's all. I mean, that's me correcting the error as well. The graph looks good, I think. They go over 1 up 3. Yeah, that all looks good. That all looks good. It's just a vertical stretch instead of vertical shrink. One word makes the difference. Fastest problem we did, I think. Number 18. Another error. Describe and correct the error here. I already see that this graph will not match up with this blue here. This x squared minus 10 means we should have translated 10 units downward, not 10 units upward. They say both graphs open up. That's true. Have the same axis of symmetry. That's true. It's here. However, the vertex of the graph of G is 0, 10, 10 units above the vertex of the graph 0, 0. Everything's proper except using up or above we would say below, and we'd say negative 10. So on number 18, we're going to mention that it is not a vertical translation 10 units up. It's a vertical translation 10 units down. They vertically translated 10 units up instead of 10 units down for a vertex of 0, negative 10. And once again, my correction, my statement of what they have also has the correction with it as well. So I'm just going to go ahead and leave that. Is that for number 18? Now, they'd have to redraw it, I guess. I guess that's something I'd have to do. If I went 10 units down, now suddenly, you'd be down here, negative 10, and then, doing that. Boom, boom. I'm just kind of messing around with it. Okay, number 19. Numbers 19 to 26. They say find the zeros of the function. Now, interestingly enough, we are currently in a chapter where we haven't solved, well, we could use difference of two squares and show that they are what they are, but they're not asking you to solve by factoring. They're asking you to solve these things by graphing. Well, they're not asking you either way, but you know what section we're in. I'll confirm from the first one, maybe the second one, that we get a difference of two squares and that we can solve that thing. When they say find the zeros, we have y equals x squared minus 1. We are going to set x squared minus 1 equal to 0 as far as finding what x values, and there are two values, what two x values we get from there to get those. However, we will graph this and we will find out what values of x makes y equals 0. What values of x make y equals 0. So let's just graph it. Let's see where it hits, and then let's confirm that that works out. So y equals x squared minus 1 starts at 0, negative 1, and then we go 1, 1, 2, 4, 3, 9, and the same thing on the other side. Now, I already immediately hit this thing. I wonder at what point I stop. I'm going to keep practicing graphing these anyway for you guys, making sure we know this. But look at where they cross the x-axis. Look at those zeros. That's what they're talking about. This x-intercept here and this x-intercept here. That's an x value of negative 1 and an x value of positive 1. And that's what those solutions are. Those are the zeros of the function. That is the answer. That is the answer. Now, I could have taken the x squared minus 1 equals 0. This is a difference of two squares that can be factored. This can be factored into x plus 1 times x minus 1, which equals 0. If x plus 1 equals 0, then x is negative 1. We already saw that one. And if x minus 1 equals 0, then x equals positive 1. Now, again, these are all solvable, it looks like, using difference of two squares if you take out a GCF. But they are kind of asking you to get the graph and work off this. You know what the problem is, though? I have some graphs that are so large for scale that they won't really fit on these particular graphs themselves. So I might have to change the scale of these numbers if you're okay with that. Depends on the problems. Number 20. Like this one, x squared minus 36. This only goes down to negative 10. So I can't actually see the vertex on this thing unless I change the scales. So y equals x squared minus 36. I would definitely at least have to go by 4s. So 1, 2, 3, 4, 5. Instead of that 5, it'll be a 20. And 6, 7, 8, 9, 10. Instead of that, it'll be 40. And then negative 20 and negative 40. I'm fine keeping the x's the way that they are. I just have to go by scales here for x squared minus 36. Negative 36 is 4 away from negative 40, so it would be right here. 1, 1, I'd go up a quarter of that because everything's 4 times larger, so I have to make these things 4 times smaller. And 2, 4 is right here, right? 3, 9 is kind of weird. 4, 16 is 4, 8, 12, 16. 5, 25 is kind of weird. 6, 36, that's, it's all the way to the top. 4, 8, 12, 16, 20, 24, 28, 32, 36, and that's right there. So we can fit these points if we do enough of those ones. And of course, we could have used the factoring and zero product property and stuff like that to get these, because this would have factored to x plus 6 times x minus 6. And if those equal 0, then x either equals 6 or negative 6. And that's our goal. To find out what x values give us a y value of 0. Because of these two here, x equals negative 6, x equals positive 6. All right, number 21. Y equals negative x squared plus 25. Oh, f of x. Same thing, right? All right, 25. Well, 25 also wouldn't fit on the scale. I could go by 5s, but that only hit me up there. Not even 2s would help. I guess I'll go by 5s. 5, 10, 15, 20, 25. That would be 50. I'm not going to have anything up there. Negative 25 and negative 50. So negative x squared plus 25. 25 is my boom. It's my vertex. The negative x squared means I go downward. I'll go 1, 1. Okay, so this will be weird. A fifth of 1. 2, 4. That's 4 fifths. 3, 9. That's 9 tenths. Boom. 4, 16. 5, 10, 15, 16. And then 5, 25. That's all the way down there, and that's what we're actually going to hit. So it kind of looks like that on the graph. Again, just from a different scale. Sometimes you have to work off different scales or really tall graphs, and I don't imagine that either of these are the best thing, but it does what it does. Now, once again, if we factor this as a difference of two squares, it would be x plus 5 times x minus 5. When set equal to 0, x would either equal negative 5 or positive 5. Those are the zeros of this. Number 22. Y equals negative x squared plus 49. I can use the same scale. I'm going to go ahead and kind of copy and paste this one in. I'll erase what I don't need. So number 22. I don't need the graph again, so I'm going to kind of get rid of that. But the scale's good, right? Okay. So f of x. I mean, you can probably imagine what this is going to be. You know, that the whole difference of two squares can kind of spell it out for you. But 49 is all the way up near 50. Remember, these are going by 5, so this is a fifth away from 50. 1, 1. Oh, man, I can't really. 2, 4, whatever. 25 down, we said, is 5 over. 25 down is 24 right there. And what's going to be 49 away? I mean, really, what's going to be 49 away? When you square 7. 6 squared is 36 down. 7 squared is 49 down. 49 down from what? From 49. So you're going to get y equals 0 when x is 7. It's really just the square of those values. Now, some of these are going to change a little bit when it comes to stretch factors. We're going to take a look at those. But that'll be at x equals negative 7 and x equals positive 7. So I can't guarantee how they want us to do it. But based on the one real-world example, the real-life application problem that we saw, and based off the section, you know, we're not solving by graphing, so to speak. By factoring. We're solving by graphing. All right, number 23, f of x equals 4x squared minus 16. I could have almost fit this from a normal one. Not quite. Let's see what we can fit and do. I'll probably scale by 2s. And I want to confirm this even with the difference of two squares with you afterward. But 4x squared minus 16, let's go. This is negative 10. We're going to go by 2s. And negative 20. And 10 and 20. So negative 16, negative 12, negative 14, negative 16 is right here. 4x squared is over 1 up to 4. Boom. Right? 4 times 1. Over 2, instead of up 4, we're going to go up 8. Excuse me. 4 times 4 is 16. So 2, 4, 6, 8, 10, 12, 14, 16. And boom, that is your x-axis. Remember, we are going by 2s on y. We're going by 1s on x. So what are those x values? They are negative and positive 2. X equals negative 2. X equals 2. Now, another way to confirm that is we could have set this equal to 0. We could have factored a 4 out of here. We get x squared minus 4 equals 0. And x squared minus 4 factors into x plus 2 times x minus 2. 4 is nothing to do with equaling 0, but x plus 2 does. X would be negative 2 here, and x would be positive 2 there. That's the result. So again, just kind of confirming that it works out that way, because it looks like all these were going to be off the edge. Except for 25. And 25, I don't know how they expect us to answer that, so to speak, without a table. Without solving by factoring. 24. We have f of x equals 3x squared minus 27. Or I'll tell you what. Maybe they didn't tell us to find a way to do this. Maybe they say, you just got to know that zeros mean where it crosses the x-axis. Therefore, if you know to set it equal to 0, you're good. They didn't give us a way. Okay, so this one with negative 27. What, can we go by threes? You want to go by threes this time? So this is 15, and this is 30. And this is negative 15, and this is negative 30. So 3x squared minus 27, these go by threes again. 3 away from negative 30 is, boom, negative 27. Over 1 up 1 times 3. Oh, yeah, and these go by threes as well. So this actually works out pretty well. Over 1 up 1 times 3 is 3. Over 2 up 4 times 3 is 12. 12 is 4 threes. 1, 2, 3, 4. So I'll tell you what, because I'm going by threes, because my scale goes by threes, and because I'm multiplying by threes, this still goes 1, 1, 2, 4, 3, 9 in its own bizarre way. Because this isn't really 1, this is 1 times 3. This isn't really 4, it's 4 times 3. But it works out that same way. What's 9 times 3? It's 9 up from here. And I go ahead and I get to hit those, boom, perfectly like that. So by my scale, I got to make it look pretty good. Maybe I could have done that for the other problems, had the scale match the A value, and then I can just count 1, 1, 2, 4, 3, 9 and be all good with it. I don't know. But those x values are negative 3 and positive 3. And I could have once again used the difference of two squares to confirm it by factoring out 3 first, by factoring out the GCF. Okay, number 25. 2 more of these ones. Hopefully they speed up after this. Number 25. F of x equals negative 12x squared plus 3. This one's interesting because we're not going to hit integers this time. Doesn't make them irrational to my knowledge. But we start up 3. Now, the verticals, it goes negative, so it goes upside down, but the vertical stretch is 12. Instead of 1, 1, it's 1, 12. What's 12 less than 3? I legit don't know. Negative 9. So, boom, we go down 9 here and 9 there. This is the sharpest of curves. This is not going to look very parabolic in my graphing realm. Actually, that's not too bad for as much curve as this thing has. Never goes completely vertical, though. Keep that in mind. But we hit here and here, and what are those values? I don't know. You go over, I don't know how much you go over before you go down 3, right? That's kind of the thing. So maybe, despite that graph, let's just confirm and make sure that we know it's somewhere between 1 and negative 1. So let's set negative 12x squared plus 3 equal to 0. Again, they're going to say plug in values. No. I'm going to factor a negative 3 out of here, and I get 4x squared minus 1 from that. Factoring negative 3 out, that is still a difference of 2 squares of 2x plus 1 times 2x minus 1. If 2x plus 1 equals 0, you subtract 1 and divide by 2. That's a negative 1. And so x is negative 1/2. So that's this guy right there. And then this is going to therefore be x equals positive 1/2. By result of symmetry and just its appearance, they look that same way. Those are the two x values at 1/2. So you plug in 1/2, you get 0 for y. And then number 26, same thing might occur here. I don't know how I'm going to graph these. I guess they go by tens this time because I have to go up to 100 basically. I have f of x equals negative 8x squared plus 98. So this is 50 and this is 100 now, and negative 50 and negative 100. So plus 98 is basically all the way up there. These go by tens, so 2 tenths, so a fifth away from 100 right there. Over 1 down 8. Down 8 from 98 is 90. Over 2 down 4 times 8 is 32. 32 away from 98. Oh my gosh. 32 away from 98. Well, it's not the answer, but 32 away from 98 is 66. So here's 50, here's 60, here's 66. This is kind of fun. Over 3 down 9 times 8 is down 72. 72 away from 98 is 26. So 10, 20, 26, like that. Now we're going to pass this on 4. Over 4, down 16 times 8. That's 128. 128 away from 98 is negative 30. So it goes down negative 10, 20, and 30 like that. So we passed it somewhere. Somewhere between 3 and 4 on both the negative side and the positive side. So let's see if we can kind of compute it by its other means, right? That's kind of the goal. Maybe it's 4.5 and negative 4.5 or whatever. Or 3.5 and negative 3.5, who knows? So negative 8x squared plus 98 equals 0. I can factor out as much as a 2. and I get x squared, excuse me, not x squared. I get 4x squared minus 49 equals 0. And that difference of 2 squares is 2x plus 7 times 2x minus 7 equals 0. So it looks like it will be 3.5 and negative 3.5. So 2x plus 7 equals 0. You subtract 2x, and you divide by 2. You get x equals negative 7 halves. That is negative 3 and 1 half. So that's that guy. And then this guy's x equals positive 7 halves for the same reason as the previous problem there. So those are the answers. So it does hit 3.5, negative 3.5. I could have tried and plug it in and see if that's what would work. I'm not using a calculator, and that's it. Okay, numbers 27 and 28, where we model with mathematics. A water balloon is dropped from a height of 144 feet. What does the function h of t equals negative 16t squared plus 144 represent in this situation? So I went over this stuff with the lecture. We've seen some of these questions in the past here. H of t, let's see, negative 16t squared, how about, represents the term, is a term which represents gravity in feet per squared second on Earth. That's true. That's kind of how that thing works. So that's the gravity portion of the equation. Basically, how fast the object, the water balloon, will drop in free fall. So there's no initial velocity, and that's just what it's going to look like. 144 represents the initial height of the water balloon. That way, at time 0, we're going to be at 144 feet. At time 1, 2, 3, 4, etc., it's going to have dropped more. That is part A. Part B, after how many seconds does the water balloon hit the ground? So this is where you did see it from a graph on their end. Yes, we can set it equal to 0, but as far as this graph goes, let me just kind of get you the idea first. So this 144 is here, and then when we have t equals 1, 2, 3, 4, etc., 1, 2, 3, 4 seconds, we're going to see what happens. So over 1, we go down 16, right? This is h of t. This is h, by the way. H of t equals negative 16t squared plus 144. So we go over 1 down 16, which is clearly not 144 yet. Over 2 down 4 times 16, so down like 48. I guess down 16 is probably not that sharp. Excuse me, what did I say? 4 times 16 is 64. So kind of quite not there. Over 3, down 9 times 16. 9 times 16 is 144. So it will end up hitting down there like that. So it is when t equals 3. Let's go ahead and solve that mathematically in case that was kind of weird as far as what I plugged in, because I know specifically what I'm doing with those. You might not. I can factor negative 16 out of here, and I will get t squared minus 9. And then that factors into t plus 3 times t minus 3. So t either equals negative 3 or t equals 3. It can't equal negative 3 because that's not a part of your domain. We drop at time 0. There is no negative time for this. So 3 seconds. And that ends up also being the answer based on that. Now, part C says, suppose the initial height is adjusted by k feet. How does this affect part B? Well, if k is positive, we kind of had this question before. If k is positive, then the water balloon is dropped from k feet higher than the previous height. And it would take more than 3 seconds to fall. 3 seconds to hit the ground. Now, I'm going to kind of copy and paste this and mention if it's negative, then the water balloon is dropped k feet lower than the previous 140-foot height, and it would take less than 3 seconds to hit the ground. That's just because you're dropped from lower, right? Drop from higher takes more time. Drop lower takes less time. And that would be part C. Number 28, the function y equals negative 16x squared plus 36 represents the height and feet of an apple. X seconds after it falling from the tree, find and interpret the x and y intercepts. So on number 28, you have negative 16x squared plus 36. As far as a graph goes, let's scale by 4s. They don't really ask us to graph, but that's not what this is all about, right? They say interpret the intercepts and all that, right? So 36, remember these are going to go by 4s, so I'll have 20 here and then 40 up here. I really don't care about this part here. I'm just going to look at the first quadrant anyway. So from here we have 36, which is 4 away from 40. Boom. We go over 1 and down 16. 16 down from 36 is 20. Over 2 down 16 times 4 is down 64. 64 away from 36 is negative 28. I guess I'll go down here for the exercise. So like that. So it's going to drop pretty sharply. And before even hitting there, right, it's going to come through and boom. We got to find out what that y-intercept is. The x-intercept on this hand, though, this is the y-intercept. The y-intercept is 0.36. That means at time 0, at time 0 seconds, the apple is dropped from the tree, falls from the tree. At 36 feet, from 36 feet above the ground. Now, we haven't solved what this guy is yet. I imagine it's probably 1.5, kind of like the other ones. We'll see. But negative 16x squared plus 36. Actually, maybe not. Negative 16x squared plus 36. Let's set that equal to 0. Let's factor out a negative 4. Factor out a negative 4, and I get 4x squared minus 9 equals 0. That's a difference of two squares that factors into 2x. Oh, that is halves. 2x plus 3 times 2x minus 3. If 2x plus 3 equaled 0, 2x would equal negative 3, and x would equal negative 3 over 2, which is time before it dropped. But here, x would equal positive 3 over 2, which is 1.5 seconds. So x equals 3 over 2 means that that's this point here. So this guy, this is the x-intercept of 1.5 comma 0, or 3 halves comma 0. So at time x equals 1.5 seconds, the apple hits the ground. Because that is when y is 0. Ground level is at 0 feet. That's the time. Okay. It's 39 to 32. Sketch a parabola with the given characteristics. I don't know, is it open-ended or what? No, it's just information. So number 29. Let's go ahead and sketch and see what these look like. The parabola opens up and the vertex is 0, 3. So it's kind of open-ended. It's very open-ended. So like that. Okay, boom. There's 29. I'm just going to do these all in the same thing. Number 30 in blue, the vertex is 0, 4, and one of the x-intercepts is 2. Okay, you know what? My 29 is too rough sketched. I need symmetry and all that. Let's just go 1, 1. Was it 0, 3? Let's go 1, 1, 2, 4, 3, 9, like that, whatever. So I'm going to go ahead and get that for number 29. All right, so number 30, we're at 0, 4, and one of the x-intercepts is 2. Now, if we hit 2, that means we also hit negative 2 right here. Now, they don't ask us what the rest of this graph is, but 2 away is 4 down. 2 away is 4 down, which means this is a standard graph. It's just flipped over in negative land, so it looks like that, and it kind of hits there. It should hit at 3, 9, 9 down from the vertex, but there's that in 30. Number 31, The related function is increasing when x is less than 0, and the zeros are -1 and +1. So the zeros are the x-intercepts, these guys here. They say it's increasing when x is less than 0, which means this graph goes upward. So, for example, I can do this and do the 1, 1, 2, 4 kind of mumbo-jumbo and hit some of those points. So I can kind of hit them like that, and that ends up being another graph. So it's increasing to the left of the vertex. No, you know what? That's not an increase. I'm sorry. I did this totally wrong. That's not an increase. I was thinking it increases. No, I just said that wrong. It's going up and upside down. There we go. It's going upside down because it needs to go up at... Here, it needs to increase when x is less than 0 like that. But it hits -1 and 1. And then number 32, the highest point on the parabola is 0, -5. So if we have 0, -5 is the highest point, that also means it goes upside down. I can once again hit those 1s. 1, 1, 2, 4, that kind of stuff. That's going to kind of look best for me. So they all have the same stretch factor, a of 1 or -1. Oh my gosh, hideous. Well, that's the highest point if it goes upside down. I'm sorry, that was 29, 30, 31, and 32. All right, drawing conclusions. Number 33. You and your friend both drop a ball at the same time. The function h of x equals -16x squared plus 256 represents the height and feet of your ball after x seconds, and -16x squared plus 300 represents the height of your friend's ball after x seconds. Write the function t of x equals h of x minus g of x. So t of x equals h of x minus g of x. We know that h of x, once again, is -16x squared plus 256. G of x equals -16x squared plus 300. When we take this and we substitute those things in, we get g of x, this is part A. We get t of x equals h of x, -16x squared plus 256, minus g of x, -16x squared plus 300. When you do -16x squared minus -16x squared, we get plus 16x squared here. And that's still a positive 256, and we subtract a positive 300, which is minus 300. So the 16x squareds will cancel out, and 256 minus 300 is 44, -44, is -44. What does t of x represent in this case? It's a constant. No matter what the time is, there's this 44. What this is telling you is your friend's ball, their balls, your friend's ball is always your ball is always 44 feet below your friend's ball in height, no matter the time. T of x represents the notion that no matter the time, since you and your friend each drop your balls, that that no matter the time, your ball is always 44 feet below your friend's ball. So what that means is that, wait, is the feet? Yeah. So what this means is that, no matter the time when they drop it, it's always, whatever, unless one hits the ground and, the other doesn't. But that's that constant. And it's negative because we took yours minus your friend's. And yours is lower. It starts off lower. It's going to stay lower. When your ball hits the ground, what is the height of your friend's ball? Use a graph to justify your answer. When my ball hits the ground, my friend's ball is 44 feet above it. Use a graph to justify it. I'm not going to use a scaled graph. But my ball and my friend's ball, let's see, maybe like that or something. My ball would be doing this, and then when dropped, it would go, remember, it's probably going straight down, but the fact that it hits that, I can copy and paste this and make my friend's ball be this one right here, which at that same time, let's make it green. Your friend's ball didn't hit the ground yet, right? This is 44 feet above. 44 feet above. So your friend's ball, maybe this is 44 like that. That's just confirming that. It's translated upward from there. 44 units upward. It's not a perfect graph by any means, but that's just the concept of it. Your friend's ball will be 44 feet above the ground. when yours hits the ground. Okay. And that's number 33. Number 34, making an argument. Your friend, maybe the ball dropper, your friend claims that in the equation y equals ax squared plus c, the vertex changes when the value of a changes. Is your friend correct? Explain your reasoning. Your friend is incorrect. A technically happens before c. So let's see how I want to explain this. I can say it out loud, but I'm going to kind of say the same things here. Your friend is incorrect. I think it's been incorrect lately. Your friend is incorrect. A represents a reflection component or vertical stretch compression, not a translation of your points. That would be regarding C. Now, I'm just giving information. I didn't mention why that is. It's because we stretch and stuff before we translate things over. The stretch component occurs before any translation occurs. I don't know. That when I plug in 0 for x, times 0 is 0, or squared is 0, I should say, times a is still 0. The a is not going to change where that thing goes. But then plus 2, it becomes plus 2. And that happens after an order of operations. I think that's just the best I can say for now. Number 35, the area A in square feet of a square patio is represented by A equals ax squared, where x is the length of one side of the patio. You add 48 square feet to the patio, resulting in a total area of 192 square feet. What are the dimensions of the original patio? Use a graph to justify your answer. I was going to say, can I just do this algebraically? So I have A equals x squared as a patio. Now this patio that has x's all around here is about to be expanded 48 square feet. That doesn't mean 48 feet in total. That means that here's another, this is 48 square feet and here's an x squared. So now you're an area of your new guy. Your new patio is x squared plus an additional 48. The total of this patio's area is 192 square feet. What we want to figure out, there are a lot of ways we can do this. I'm trying to think how I'd best explain it to you. We need to do one of two things. We can either graph y equals x squared plus 48 and see when it hits y equals 192, or subtract 192 from both sides, which would give me, I can't do that math right now, 84, 40, 144, 144, and figure out when I hit 0 here. So graph y equals x squared minus 144 and just see where it hits the x-axis. Because if I subtract that over, set it equal to 0, then I'm trying to find my zeros off of that. So that would also work. So either graph it at x squared plus 48 or x squared minus 144. And I'll tell you how this thing works here. 144 is also 12 squared. So this thing's going to be hitting, all the way here. At negative 144 is the vertex. And then once I hit x equals 12 and negative 12, it's going to, that parabola-wise is going to hit both of these. Now, x can't be negative. So the graph justifying my answer is that 12 squared is 144. It's going to be 144 units up from there. That's how this thing works as far as these, right? Over 12, up 144. So this is at 12 comma 0 and negative 12 comma 0. Remember, distances cannot be negative, so in this case, x would equal 12. They ask what the dimensions are of the original patio. Dimensions are 12 feet by 12 feet. Does that make sense? 12 feet by 12 feet is 144 square feet. That would have been the area of the original patio. When I add 48 square feet to the 144 square feet, I get 192 square feet. That seems to make sense as an answer. So that is the answer. The dimensions are 12 feet by 12 feet. Okay, number 36. How do you see it? The graph of f of x equals ax squared plus c is shown. Points A and B are the same distance from the vertex of the graph of f. Which point is closer to the vertex of the graph as c increases? If c increases, that means we're getting up higher and higher because they're saying that c is positive, or we're adding c. And if c increases, it's getting larger and larger. It's kind of a weird question. They're not asking why that is. It's just it gets closer. As c increases, which point is closer to the vertex? Point A is closer to the vertex of the graph. They don't ask why, but you can understand why. It's going to go up more. They're just asking to make sure you know how C works as far as a component for this thing. Pretty easy question overall, but as far as that, you just need to make sure you have knowledge. Number 37, describe two methods you can use to find the zeros of the function. F of t equals negative 16t squared plus 400. So this is interesting because they also say check your answer by graphing. The reason I say this is interesting is because it seems like they're giving me leeway to solve this algebraically. I was under the impression I had to do everything by graphing, not just by the example that they gave us, but anything else. I don't know if that's what they're saying. They say check it by graphing, almost like that's a third option. I don't think we solved using square roots yet. That doesn't happen until chapter 4. So I'm going to be doing method 1 is factoring, unless they're talking about the different ways we can talk about the graphs. But method 1 is factoring and zero product property. We need to find out where the zeros are, so we set this guy equal to 0. Negative 16t squared plus 400 equals 0. I can factor out a negative 16 from there, and I get t squared minus 25. So that factors into t minus 5 times t plus 5. And that gives you a t value of 5 and a t value of negative 5. So that's method number 1, factoring and zero product property. Method number 2 is graphing, or there's a method 3, which is solving using square roots, but we don't do that till chapter 4. So I assume. So method 2 would be solving by graphing, but also maybe using a table. Method 2, I don't know, say table? Because that's technically what they did on that one word problem. I know they graphed it, but they used a table. So let me just plug in some of those numbers and show you what we get. T and f of t. When you substitute in 0, you get 400. You substitute 1, you're doing 16, you're down. We're going down from 400. 16 times 1 is 16, so we're going down to 384. Plug in 2, you go down 16 times 4, you go down 64. Which is 336. I don't know why I had so much trouble with that. 336. You go down 3. 16 times 9, right? 3 squared is 9. 16 times 9 is 144. You go down 144, 256. You go down 4. Sorry, this should have said negative 5. No. You go down 4. 16 times 16 squared, so down 256. That's 144. And you go down 5. You have 16 times 25, which is 400. 400 minus 400 is 0. So boom, that guy locks in. And of course at negative 5 as well. Also at t equals negative 5. You know, that's just how that works. Using the table, check it by graphing. I mean, we have 400 way up here. Well, let's make it even higher. 400, 300, 200, 100, and 0. I mean, this ain't the best graph in the world, but this is just the idea. That's where it's going to be hitting. Right there. And right there. Sorry, I just don't know how they want us to answer this. This is the thing based off graphing, and I don't necessarily have the scales in my head there. Solving by factoring is good, using the table stuff. Now, my table was me. I didn't plug these in by, like, plugging them in. I said 1 squared is that, times that, minus that, and all that kind of stuff. It's what I'm doing, but I have kind of a different way of knowledging it in my head. 4 more problems to go, and I want to get through them. So, number 38. The paths of water from 3 different garden waterfalls are given below. Each function gives the height in feet and the horizontal distance of the water. So, height. So, depending on how high the waterfall goes, it's how much the water will fall away, I guess, from your thing. So, height is equal to these things here. Which waterfall drops water from the highest point? So 38, we have waterfall 1, h equals negative 3.1 d squared plus 48, 4.8, excuse me. Waterfall 2, h equals negative 3.5 d squared plus 1.9, and w3, h equals negative. Okay, whoops, 1.6. Which waterfall drops water from the highest point? These are all upside down parabolas that have a vertex at their C values. So waterfall 1 has the highest vertex. Therefore, it drops water from the highest point. I guess the water shoots out that way. So for part A, waterfall number 1, waterfall 1. From the highest point. Sorry about that. It's part A. Part B, which waterfall shows the narrowest path? Narrowest path will be the one that's most vertically stretched. That'll be waterfall 2. Because, now they don't ask me to explain, I'm going to tell you. It's because it has a most vertical stretch. Vertical stretch is the narrowest path. Waterfall 2 follows. I'm trying to imagine that this picture is telling us what we're talking about. I guess it's coming off the side. Follows the narrowest path. That's because the A value is the biggest. The biggest negative, I should say. Part C, which waterfall sends water the farthest? I just want to make sure that D, I'm not thinking of this inversely. I think that's all right. Which waterfall sends water the farthest? We have to figure out which one gets the largest D value before we hit 0 on these. I almost want to go, because I don't want to like graph these the way I generally would. I almost want to use a graphing calculator and see which one just hits the farthest before we go and get there. This is one where I'm really not interested in a table as much as seeing the graphs or kind of comparing them. So give me a moment. Let's go ahead and do that. Let's do waterfall 1 is negative 3.1 d squared, in this case x squared plus 4.8. The next one, let's make in bold, which will be negative 3.5 x squared plus 1.9. And the third one will be negative, let's see what different kind of thing I have. Not an inequality. No. Dotted. The third one will be negative 1.1 x squared plus 1.6. All right, let's see. Even just from here. We want to see where they kind of hit. So that's the first one. Second one, no, not as far out. The third one, oh, we're going to have to zoom in on this. Oh, I can't tell if the dotted one, let's zoom in on one of these. I can't tell if the dotted one or the other one actually gets closer or has more stuff. Let's see. That one hits there. That one hits. Where's the dotted one? There. Oh, waterfall 1 shoots a little farther out. It gets a little more distance based on its height. Which waterfall sends water the farthest? It's a close one, but waterfall 1 does. Waterfall 1. I guess it being just a little bit higher up sends water the farthest. Oh, my handwriting's getting really bad. I've been graphing so long I can't write anymore. So sorry about that, y'all. All right. Oh, you can't even see what I'm writing. Sorry about that. Man, imagine how long it would have been on that thing and had that. My handwriting is not too good on that one. All right. Number 39. 3 more. 2 acorns fall to the ground from an oak tree. One falls 45 feet while the other one falls 32 feet. That's not outward. They mean downward. For each acorn, write an equation that represents the height in feet as a function of time. So let's use, I don't know, f of x and g of x or something like that. f of x for 45 feet. We're going to use that 16 thing. Negative 16x squared and plus 45. And the other one is going to be g of x. And we'll call it... sorry, I got an email. Negative 16x squared plus 32. So that's part A. Part B, describe how the two graphs of the two equations are related. Okay. They each share the same force of gravity. And they are both dropped at the same time. One is 13 feet above the other, including when the second one hits the ground. So the second one hits the ground, the first one would be 13 feet above it because the 45, basically. And this is how it works. That's how it works. Number 40. One of two classic problems in calculus is to find the area under the curve. That is very true. Approximate the area of the region bounded by the parabola and the x-axis. Show your work. I could do it algebraically. Okay. I don't know what they specifically want me to do here. We could talk about triangles. One thing in calculus is you can approximate things by looking at areas like with triangles instead. What if I found the area of this triangle, right? That's pretty close to this. It's an approximate thing. So let's find the area of this triangle instead. And this triangle has a height of 4 and a base length also of 4. This is going to be a little bit less than the answer. They also use a lot of trapezoids, but I'm not getting into, we're not talking about areas of trapezoids, things like that. So this is an underestimation of the area. The area of that triangle is 1/2 base times height. So 1/2 4 times 4, which is going to be 8 square feet. 8 square units. Okay, that's my answer. Now listen, it's going to be more than 8 square units in reality. If I were to use calculus on this, I would integrate. You have no idea what this is going to be. From x equals -2 to x equals 2 of negative x squared plus 4. Shoot, I didn't forget how I write this. Do I write dx? I can't remember how I do this anymore. Negative 1/3 x cubed plus 4x plus c. Shoot, I have not done this in so long. I haven't done this in like high school, since like high school. Negative 1/3 2 cubed plus 4 times 2 plus c minus negative 1/3 negative 2 cubed plus 4 times 2 plus c. C's cancel, whatever. So 2 cubed is 8. So negative 8/3 plus 8 minus negative, oh my gosh, that's a lot of minuses. Minus negative So minus another 8/3 minus 8. I must have done something wrong. Negative x squared plus 4. 1/3 x cubed. I don't know if this is worth me saying what I'm saying for all this stuff. Subtract one from the other. Negative 2 times negative. I don't know, man. I could come up with this, but I'm having so much trouble with it to begin with. Yeah. That would give me a negative answer. That's the only problem here. So there's got to be some other trick to this that I'm not seeing for the negatives. I don't know, man. I'll do my calculus later. This is too old school for me. Doing something wrong there. I'm not sure. I'm not doing calculus right now. I should be able to solve that. I'm sorry that I didn't do that correctly. Number 41. Critical thinking. A cross section of the parabolic surface of the antenna shown can be modeled by y equals 0.012x squared, where x and y are measured in feet. The antenna is moved up, so the outer edges of the dish are 25 feet above the x-axis. So I guess it's going to like move up there. Where is the vertex of the cross section located? Explain. So the antenna is moved up, so the outer edges are 25. Oh, the outer edges are 25 feet above. So right here. So before the outer edges look like they're at 20 feet, and now they're going to move up here to 25. So they move up 5 feet plus 5 feet. Therefore, the vertex of the cross section, you don't have to worry about the equation. I have to drink water again. The vertex is located 5 feet above the ground? What's the original? It moves up 5 feet higher. They said to explain out hiccups. This is because the edges were at 20 feet, and 25 feet is 5 higher. 20 feet. Higher than it was before. Okay, I'm gonna drink some water and then I'll get my closure in case I want to say anything else. Okay, and while I was drinking water, I just looked back at my numbers here and I cracked what this problem is here. This is a +8. That's minus -8. So I didn't see that. So that should be a +8 here. So this guy, calculus-wise, you got 16 minus 16 thirds. Don't even worry about this. 48 thirds minus 16 thirds is 32 thirds. 32 thirds, which is exactly 10 and 2/3 square units. So that's the exact one, whereas we approximated 8 square units. That was definitely an under approximation when all was said and done. But yeah, that minus negative should have been a plus, and all the rest was good from there. All right, guys, that ought to do it for this one here. This is Mr. Robinson. Thank you so much for watching. I know this one got a little screwball-y for a lot of different reasons. One, I can't guarantee how they want us to solve all the things. It's all about graphing. Their examples had graph things with them as well. So, I mean, why don't we just graph as much as we can? And just number two, I don't know. If I have some other worksheets that I do eventually with solution guide things or some old ones, then you'll see kind of what I do when it comes to graphing in general. But this is how I answered their questions. So thank you so much for watching here. We're going to hit section 3.3 next, and then we have a little quiz review portion as well to do. Thank you guys. Take care. I will see you in the next one.